Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be doing a quick overview of nuclear chemistry. And so this is going to be a lot very different from what we've looked at previously. So I always like thinking about chemistry as focusing in on chemical reactions. So making and breaking bonds, taking atoms, turning them into molecules, and moving those molecules around. And all of these properties focus exclusively on the behavior of electrons. It's sharing electrons that make a bond. It's moving electrons that make electrochemistry. However, it turns out there is more to the world than just electrons, as painful as it is for me to say. In comparison, we're in this last unit going to focus on nuclear chemistry. So in this case, we're going to be looking solely at the behavior of nuclei. So these are going to be our protons and neutrons. And one of the big features of nuclear chemistry is going to be the idea that with enough energy and enough effort, you can actually go ahead and study how nuclei can change and interconvert. So the first thing we need to establish is what is the structure of a nuclei and try and help figure out what makes a stable nucleus. Once we have an idea of what's stable and what's unstable, we can try and look at the processes by which the number of neutrons and protons can change, how I can go ahead and change the nuclei into something else. And while we do this, we're going to bring in a lot of topics we've hit before, including kinetics. So the first thing we need to do is establish how we define a nuclei. And we end up doing this using what are called atomic term symbols. So for here, we're going to ignore the presence of electrons. So I won't represent any ionic charges in this upper right corner like we have before. If you want a quick review of atomic structure, please feel free to take a look at the video links below. But we can really define our atomic term symbols with three key features. First is our element or nuclei type. So this will be represented by our classic elemental symbols. So U is for uranium. Then we need to include the atomic number. This is also the same thing as the nuclear charge or the number of protons. Now, it is worth noting that this number defines the element we're examining. And so a lot of people will, as you see below with boron, neglect to include this atomic number, and that's okay. However, it's going to become very useful in the subsequent chapters that we are able to easily keep track of the number of protons in a system. So I'm going to tend to include this in everything we do. Then in the upper left-hand corner, we have our atomic weight. So this is the total mass of protons plus neutrons, really just telling me how many particles are in my nuclei. So again, our atomic number is going to be the same thing as the number of protons. That means that everything else is going to be my neutrons. So I can find the number of neutrons by taking the difference in between my atomic weight and my atomic number. Now, one of the big features is that while a given atomic number defines which element we're looking at, many elements have multiple different isotopes or numbers of neutrons. For example, we've got boron 10 and boron 11, both naturally occurring boron isotopes. Now, one of the interesting things about this is that while boron has 5 protons, that means that boron 10 will have 5 neutrons, but boron 11 will have 6. And it's worth noting that both of these will be present, but both of these might not be present in equal amounts. And so we have to try and figure out what makes one element more or less likely or more or less stable than the other. And that's going to be a major focus of this chapter, is looking at the stability of isotopes. And so it turns out that if I'm looking at something like hydrogen, it has 2 stable isotopes. The first is just a single proton, no neutrons. So the atomic number and mass are the same. And this defines what we call hydrogen. However, we also have something called deuterium, where we have 1 proton and 1 neutron with a total mass of 2. And this has its own special name. And it is worth noting both of these occur naturally, though hydrogen occurs in a much higher abundance. However, there's also one unstable isotope of hydrogen, and that's called tritium. And tritium has 2 neutrons. And it is worth noting that all 3 of these isotopes occur frequently enough that they're often referred to by name or symbol. So H represents hydrogen, D represents deuterium, and T represents tritium. And it's worth noting that if I end up having tritium present in a sample, it will slowly tend to break down to form a different element, whether it's helium, hydrogen, or deuterium, which we're going to focus on a little bit more later. So general rules of what makes a stable nucleus. The first important idea is that in general, as I tend to have more protons, as I go on from hydrogen to things like helium, lithium, beryllium, I'm going to need more neutrons to help hold the system together. And you can kind of see this in this chart, where we have the number of protons on the bottom, number of neutrons on the left, and we have a list of all of the stable isotopes along the middle. And generally what you tend to see is that as I gain more protons, I need more neutrons to hold the system together. So for low elements, so up to a 20 protons, a 1-to-1 ratio of neutrons to protons tends to work pretty well. However, after this point, we tend to need a lot more neutrons. And the way I tend to like thinking about this is building a nucleus is a lot like building a brick wall. The protons are our bricks. They define what our wall is. But as I gain more and more bricks, I need more and more mortar to hold the system together. If I have too many bricks but not enough mortar, my wall falls down. If I have too much mortar but not enough bricks, the system becomes rather clumsy and isn't stable either. However, if I only have 2 bricks, I only need a little bit more of mortar. However, as I get to more and more bricks, then I need more and more mortar because I don't need to cover just 1 or 2 sides. I need to cover all 4 sides and help insulate the system from more directions. And this is really what neutrons are thought to do, is protons hate each other because they're all positively charged. Neutrons help glue those protons together and help reduce the repulsion. However, as I try and cram more protons into a place, those neutrons help increase the stability. However, it is worth noting that we are dealing with quantum particles, which means that they do tend to have certain rules very similar to our octet rules. And there are certain numbers of protons or neutrons that are going to be much more stable than others. The most commonly occurring and the most stable of which are called magic numbers. And so these are essentially highly stable arrangements of our nucleons, and they tend to follow fairly similar sorts of patterns as what we saw with the electrons. It turns out that having 2 protons or 2 neutrons is really good. Having 8 is kind of like having a full octet shell. 20, 28, 50, 82 are all very good numbers for both protons and neutrons. However, after this, we see a slight divergence, and the next magic number for protons is 114, and we've never been able to build anything past that. However, there are some hypothetical islands of stability of stable numbers of high protons. And we see a very similar pattern when we're looking at neutrons. And it is worth noting that these magic numbers do tend to affect our everyday lives, as some of the most common elements that we encounter have magic numbers for both protons and neutrons. So for example, helium has 2 protons, 2 neutrons, and there's a reason why it is one of the most abundant elements in the universe. And we're going to be seeing a lot more of it as we proceed through this chapter. However, oxygen, which makes a lot of life possible, also has 8 protons and 8 neutrons. So again, it hits this next island of stability. And we have other things like turns like that calcium is quite abundant because it's a 20 and 20 with a most stable isotope of 40. However, you can take this all the way up to lead, which is the second heaviest stable isotope in the world. And this has 82 protons and 126 neutrons, again, hitting that double. And the only element heavier that is stable is bismuth, which only beats it off by 1 proton, which helps illustrate that even if you aren't at one of these magic numbers, if you're fairly close, you're at least gain a little bit of residual stability. The further away you are from one of these magic numbers, turns out the less likely you are to occur. However, there is some, and one good example is something like technetium. It's sitting in this big open space in between 28 and 50, and it turns out it doesn't exist in nature, not in any number of neutrons. And this also emphasizes another key point. It isn't just the number, the magic numbers that matter. It turns out that nuclei also tend to prefer to have even numbers of both protons and neutrons. And notice that all those magic numbers were even. And these are going to be the most stable elements. And so in general, if an element has an odd number of protons, it's very unlikely to have an odd number of neutrons. Only 4 elements do that. And it turns out there's only 50 stable isotopes for any sort of odd-even combination, giving us, for odd proton elements, only 54 stable isotopes. So if you have an element with an odd number of protons, it's less likely to have multiple different stable isotopes. If you have elements with even numbers of protons, they're much more likely to go through even numbers of neutrons, with that corresponding with the majority of natural occurring isotopes, over 50%. However, it is worth noting that even with those 4 elements that have odd numbers of both protons and neutrons, they all have one general common thread. They're the lightest 4 odd-numbered elements: hydrogen, lithium, boron, and nitrogen. And you'll notice another key feature of these is that they all keep that 1-to-1 ratio that is very favorable for lighter elements. So deuterium, lithium, boron, nitrogen. If you have an odd atomic number that isn't one of these, you're not going to have an odd number of neutrons. We can guarantee it. And in general, if you have to choose in between having an odd number of protons or an odd number of neutrons or an even number, the isotope with an even number tends to be a little bit more stable. So next time, we're going to go ahead and look at how unstable isotopes can rearrange themselves, put their act together, and make something better. Until then, take care.